Hey, welcome to Unit 6, Thermochemistry. Really on the home stretch, the last couple of units coming up. Our last unit will be all called thermodynamics together. Today we're learning the first of the thermodynamic quantities, enthalpy, learning about calorimetry a bit, and then something called Hess's law, and then a couple different types of math problems. So a little break after the acids and bases. I find this much easier. The math is a bit simpler. We're going to use some formulas and stuff. Um, but I don't think it's too bad. Let's go ahead and get started. All right. Like I said, today we're talking about enthalpy, calorimetry, Hess's law, and the thermochemical equations. The first of a couple we're going to learn. Energy is, energy has a lot of different definitions. And depending what class you're in, depending on what topic in that class you're in, it's going to be different. Today, what we're going to think about with energy as is the capacity to do work or produce heat. The law of conservation of energy is important. It says energy can be converted from one form to another, but cannot be created or destroyed. The total energy content of the universe is constant. Which has a lot of applications. Like that means no matter what happens, the total amount of energy can never actually increase or decrease. So you could actually set up a formula to calculate the total amount of energy in the entire universe, and that number would always be constant. But that'd be a really long formula. All right. A couple different types of energy. We're going to kind of breeze over this. This is more physics stuff, but it is kind of important for us. Potential energy is the energy due to your position or your composition, meaning it's energy that you kind of have stored up. So, like a chemical bond has like potential energy sometimes because it's basically storing energy that can be released at a later time. You could think like glucose molecules in our body. We use them to produce ATP, but we can save them for when we need them so we don't have to constantly be eating glucose molecules. Those have potential energy. Kinetic energy is the energy of the motion of objects. How much energy does something have because it's moving fast? That depends on its mass and its velocity according to the kinetic energy formula below there. Not something we're really going to have to solve, but you should know that kinetic energy increases if you increase the mass of an object or its velocity. No volume. Heat involves a transfer of energy between two objects due to a temperature difference. This is main type of energy we're worried about today is the energy of heat. Heat and energy are pretty much synonymous. They mean pretty much the same thing. Heat flows from hot to cold. So a hot object will radiate heat and lose it, flowing towards a cold object. Cold doesn't move, heat does. Um, that's why you can't. Defining what cold is really difficult by itself without using the word heat in it. Coldness is just a lack of heat. Heat is the actual physical thing we can measure, it's energy. Coldness is just the absence of heat. Temperature is a property that reflects the random motions of the particles in a substance. Okay, a couple more definitions before we get into our math. The system and the surroundings are an important distinction and definitions. The system is just the specific part of the universe, a weird way to phrase it, but has a reason, on which we want to focus our attention. So it is like our beaker or test tube that we're doing our reaction in, or it is our cup of water or cup of coffee where we're trying to calculate the heat or something like that. And then the other word is surroundings, which is literally everything else in the universe. Surroundings would be like if I'm losing heat in my system, it's going to the surroundings or vice versa. All right. Couple types of reactions. Endothermic reaction is a reaction where heat flows into the system. Another way to think about that is heat is a reactant. You're going to add heat to the reaction to make it start or to increase its speed or as just one of the reactants you need. Energy is absorbed from the surroundings and converted into chemical potential energy called bond energy. This means the temperature of the surroundings decrease. So an endothermic reaction adds heat from the surroundings into the system that'll lower the temperature outside. Or not like significantly, but lower the temperature of the surroundings. An exothermic reaction is the opposite. Energy flows out of the system. When those things react, when the chemical potential energy, when those bonds react, the excess is converted into heat. This is a far more common type of chemical reaction, is an exothermic, one that produces heat. Things like combustion reactions are always exothermic. Acids and base reactions are usually exothermic. They produce heat. The temperature of the surroundings will increase. Okay? A key thing, according to the law of conservation of energy, energy gained by the surroundings must equal the energy lost by the system, or vice versa. So if I add 50 kilojoules of energy into my system because it's an endothermic reaction, that means the surroundings lost 50 kilojoules, my system gained 50 kilojoules, the net change has to be 0. Internal energy is the energy from the system's point of view, from where my reaction is taking place. Endothermic process, heat is going to be a Q, is going to be a symbol we use for heat all today, and Q will be positive for an endothermic reaction. You have to add in heat. So if you add heat, it's positive. We're using the system's point of view. Exothermic means heat is negative. The system loses energy in an exothermic reaction. Energy is a product. Okay. A change in enthalpy. Okay. Enthalpy is our first thermodynamic quantity we're going to talk about today, and it tells you a couple of different things. It tells you kind of how the energy changes in a system, but it's mainly used for this relationship I'm having you write right here. Okay. The change in enthalpy in a reaction is the enthalpy of the products minus the enthalpy of the reactants. And all it really tells you, if change of H is a positive number, that's an endothermic reaction. So if you calculate the enthalpy and it's positive, you have an endothermic reaction. If the enthalpy is negative, you have an exothermic reaction. Okay? There'll be a couple different ways to calculate enthalpy that we'll kind of learn throughout today and actually into the next unit as well. Okay, but enthalpy, main thing you need to remember, tells you if something is endothermic or exothermic. Positive enthalpy, endothermic. Negative enthalpy, exothermic. Enthalpy is just a really fancy way to say bond energy or heat. And there's a couple different types we're going to learn. Okay. For a particular reaction, enthalpy, change in H values, are linked to the coefficients in the balanced equation. Okay, so let's take a look at this reaction before we read all this wall of text. I have 1 CH4 plus 2 O2s yields 1 carbon dioxide and 2 water molecules. It's just a normal combustion reaction. We have this extra information over to the right, our enthalpy. I have my change of H is equal to negative 890 kilojoules. It's a negative number, which means it's exothermic, which means it's making this much heat when it reacts, which makes sense because this is a combustion reaction. Fire makes a lot of heat. Okay. What this means, though, is when this reaction occurs exactly like it's written here, when 1 mole of CH4 reacts with 2 moles of O2 to produce 1 CO2 and 2 H2Os, it produces exactly this much heat. Okay. If you have any other numbers here in a reaction, this number will be different. This is the enthalpy value that correlates exactly to how this is read. Okay. We can use unit conversions to calculate the enthalpy with slightly different numbers. And I'll kind of show you what I mean by that. This is our first way we're going to calculate the enthalpy of something. So here's the same reaction, and we're going to do 3 different practice problems answering about how much energy is made from some different situations. Okay, I'm going to take a second. I'm going to write down this reaction here. Let's go. Okay. 1 CH4 plus 2 oxygens yields 1 CO2 and 2 H2Os. Write down my enthalpy as well. Okay. This enthalpy applies to this entire reaction, applies to each of these substances. Okay. What it means is, let me try to focus this here. What it means is when I use 1 mole of this is the enthalpy associated with it. When I consume 2 moles of oxygen, that's how much enthalpy it uses. When I produce 1 mole of carbon dioxide, that's how much enthalpy I produce. When I produce 2 moles of H2O, it makes this many. So we can kind of just use this like a stoichiometry fact. I can find the enthalpy when I start or end with any amount of these products or reactants. So here I'm starting with 2.56 moles of methane, which is CH4. Okay. Well, I know when I react 1 mole of methane, it makes negative 890 kilojoules. So if I react 2.56 moles of methane, I'm just going to multiply that by negative 890. That equals negative 2280 kilojoules. And that's it. That's the answer. 1 mole of methane reacting produces that much energy, so 2.56. I'm just going to multiply by that number. We can kind of set this up like a unit conversion, and I'm going to show that as well, like a more traditional stoichiometry. Okay. So I have moles of CH4 on top, so I'm going to put it on bottom to cancel. And what I want to know is the, let's say, kilojoules of this reaction. This reaction up top, what this means is, when I react 1 mole of CH4, it produces negative 890 kilojoules. Multiply across, and it's going to be the same answer, of course. Okay, that's essentially how you would see the work shown for this. Okay, moles and moles cancel. 1 mole of CH4 is associated with negative 890 kilojoules. Next reaction. So I'll call this A, B, and C, but they're not really numbered on yours. But second question here, we have how much energy is produced from 39.5 grams of water, H2O. Okay. Water is included in this reaction. It's a product this time. We're going to use the same strategy. Our conversion, basically, 2 moles of H2O, because there's a 2 here, equals this number. 2 moles of H2O equals negative 890 kilojoules. Well, I don't have moles here, I have grams, but I can turn that into moles. And then once I have moles of H2O, I just multiply it by that number. So let's do that. 39.5 grams of H2O. Grams of H2O on the bottom to cancel. About 18. Okay. I'm just going to combine them all into one step here. I have 1 mole of H2O. So I'm going to put moles of H2O on the bottom to cancel. What I want to find is kilojoules. So I'll put that on top. I'm going to plug in the numbers from this expression we just talked about. 2 moles of H2O equals negative 890 kilojoules. So basically, it's like a stoichiometry problem. We're just adding on this last step. The kilojoules, which you can't see where I'm pointing, comes from any of those 4. So I'm going to multiply and divide across here. I get smaller number this time, negative 975 kilojoules. Okay. So this time I had grams, I just turned it into moles, and then once I had moles, I just multiplied it by this number, but I do have to remember 2 moles of H2O are needed for this reaction, so I divide it by 2 as well. Last, we have part C. It's going to be very related, except I'm looking for mass of oxygen, so I'm looking for grams of oxygen. This time it's telling me I use 435 kilojoules. Okay. Out of room. Okay. So this time I'm starting with kilojoules. I need to find grams of oxygen. So let's see what I can do with that. 435 kilojoules. Okay. Kilojoules on bottom. To cancel. What can I turn kilojoules into? Well, I look at my reaction here. Kilojoules can just turn into any of the moles of any of these 4. It's just like another product or reactant in this reaction. So I'm going to turn it obviously into what I want to find, O2, moles of O2. Okay, getting my numbers right. My kilojoules is still at negative 890. My moles, my coefficient of moles in my reaction is 2. So I'll put a 2 there. That gives me moles of O2. I want grams of O2, so I'm just going to convert moles of O2 into grams of O2. 1 mole is about 32 grams. Multiply all that across, and I get 31.3 if I round grams of O2. Here are those 3 problems worked out. Some of these you might be able to work out kind of in your head without showing the work. It's fine. Here's how I would do the stoichiometries, though, if that makes more sense to you. Super professional here. Phase change. A phase change diagram shows you how the state of matter of a substance changes with temperature. On the next slide, how does water change states with temperature? So we're going to look at water on the next slide, a picture. Notice the 2 flat horizontal lines in particular. Why doesn't the temperature change in these points? Okay. Here is my phase change diagram. On my x-axis, I have heat. As I go to the right, I add more and more heat. I'd expect the temperature to go up as you add more and more heat. On the y-axis is my temperature. I have 0 or negative actually would be at the bottom, and then it goes up. My melting point is marked here. Boiling point is marked here. For reference, the boiling point of water is 100 degrees Celsius. Melting point is 0 degrees Celsius. Okay, so as I add heat, I'm starting over here on the bottom left. I have ice. I have very, very cold ice that's way below the melting point. So I'm going to add heat to that ice, and that ice is going to slowly start to warm up. The temperature increases and increases and increases until it gets to this point. At this point, I'm going to continue to add heat, but the temperature isn't increasing. And this happens at the melting point. So I have my ice that's heating up and heating up and heating up until it gets to the melting point, 0 degrees Celsius. And then as I add more and more heat, the temperature stops changing. But the ice, if you look at it, will actually start changing form. The ice, as you go and add more and more heat, even though the temperature doesn't go up, is changing. It is melting into a liquid. So here, at this point on the graph, I have a solid ice at 0 degrees Celsius. After I add more and more heat, I actually have liquid water at 0 degrees Celsius. Once all of my ice is melted into water, as I add more and more heat now, the temperature does start to rise because all of it is a liquid. I heat up my liquid and heat it up and heat it up and heat it up until it reaches the next key temperature, the boiling point. At the boiling point, I have to keep adding heat and adding heat and adding heat. The temperature is not changing, but my substance is. My liquid is turning into a gas. It is vaporizing or boiling. And I'm going to keep adding heat and adding heat, adding heat until all of it has vaporized. Once all of it is vaporized, I now have a gas. And I can continue to add heat as much as I want to heat up this gas, and it'll continue to stay as a gas as long as I heat it up. That is the phase change curve of a liquid, or of water specifically, I guess, but of any substance would follow this. I can also follow it backwards with condensing, going from a gas to a liquid, and freezing, going from a liquid to a solid. I have to remove heat or go to the left to make that happen, though. We're going to talk about this when we talk about calorimetry. The important thing to take away from this graph is at the melting point, I have to add a specific amount of heat, not to change the temperature anymore, but to actually change the substance from a solid to a liquid. It takes a certain amount of heat just to melt something, not even increase its temperature. It also takes a certain amount of heat to vaporize something without changing its temperature. As you add heat to water, the temperature goes up, but the temperature doesn't increase at 2 points, the melting point and boiling point. You start with ice and add heat until it reaches 0 degrees Celsius. Once the ice reaches 0 degrees, the heat we add doesn't directly lead to a temperature increase. The heat is used to melt the ice and turn it into water. The temperature doesn't increase until all the ice is melted and becomes water. We can calculate the amount of heat we need to melt, boil, freeze, or condense something, and they use the heat of fusion and heat of vaporization. The heat needed to melt the solid into a liquid is called the latent heat of fusion. Its symbol being H with a little f. The latent heat of fusion of water is 334 joules per gram. That means to melt 1 gram of water, it takes 334 joules of energy. The heat needed to boil the liquid into gas is called the latent heat of vaporization. Vaporization means to turn something into a gas. HV. The heat of vaporization of water is much larger than the fusion, 2,260 joules per gram. To turn 1 gram of liquid water into gaseous water vapor takes 2,260 joules of energy. Okay? It takes a lot more energy to vaporize something than it does to fuse something, which kind of makes sense. Think about boiling a thing of water on the stove. If you had a big pot and you left it on the stove for an hour, 2 hours, 3 hours, the water level would go down on that pot, but it still wouldn't boil right away. Like, it takes a long time to boil water. Just to heat it up to boiling takes a long time, but it takes even more time for all of that water to boil away. But ice melts relatively quickly, like just at like room temperature, it's not even that hot, it'll melt like really fast. It takes a lot more energy to vaporize something. Now, we can calculate the exact amount of heat needed for that using these two formulas. Okay. To melt a solid uses the heat of fusion. Q is heat equals mass times the heat of fusion. So whatever mass of it you have 100 grams or 1,000 grams, you plug that in for mass, times that constant, and that's how much heat you need. To vaporize a liquid, same thing, but you use the other constant, the heat of vaporization. Also, if I want to freeze or condense something, those two things remove heat. I use the same formula, but I just slap a negative sign on there because I'm removing that much heat. Okay, so let's do these two examples real quick. How much energy is needed to boil 500 grams of water? How much energy is needed to freeze 500 grams of water? All right, squeeze it in here. It's pretty easy. So I want to boil water. I want to freeze water. I have 500 grams with both of them. Okay. For boiling, Q equals M. Boil means vaporization. I'm going to use the HV constant. To freeze something, Q equals M. To freeze or melt something, I use the other one, HF. Now, boiling adds heat, so this should be a positive number. Freezing removes heat, so this is actually going to be a negative number. Okay, so over here for boil, Q equals mass, 500 grams, times the HV we just talked about on the last slide, which was the 2260. I believe, let's check. 2 slides ago, HV is 2260. Yep. Plug this into my calculator, 500 times 2260. Real big number, it is 1,130,000. 1,130,000 joules. With really large numbers like this, you likely would see it written as kilojoules. So it'd be 1,130 kilojoules. Both those answers are the same. Now for the freeze one, I'm going to make my Q negative. My mass, when I freeze this one, still 500. My HF is that other number, 334. Okay, so this time I'm going to multiply a slightly smaller number. Negative Q is that, or Q is negative 167,000 joules, or kilojoules divided by 1,000. That's how much heat I need for those two things to happen. Q is negative. That just means I'm removing that much heat. Boil is positive. That just means I'm adding that much heat. So this negative sign or positive sign just tells you mainly direction. Am I adding heat to my system? Am I removing heat from my system? All right, our next topic is called calorimetry. It's the science of measuring changes in heat and changes of temperature. Specific heat is a value we're going to use, and it's going to have the symbol little c. The specific heat is basically a substance resistance to a change in temperature. It's the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So some substances have a very high specific heat. It takes a ton of heat to raise their temperature or lower their temperature, to change their temperature at all. Substances with a low specific heat, it's way easier to change their temperatures. One thing you might learn about if you remember way back in like freshman biology or something, one of the properties of water was that it has a very high specific heat. Here are common materials and their specific heats. Liquid water at the top, 4.18. The unit is joules per grams times degrees Celsius. Not super important, but just worry about the number. 4.18 for liquid water. Solid water, or ice, has actually a smaller specific heat, 2.11, and water vapor even slightly smaller than that. But all of those are quite at the top of this chart. Common substances that we use, they have the highest specific heats. It is important. These top 3 are very important. I would recommend writing them down in your notes real quick. Liquid water is 4.18. Solid water or ice is 2.11. Water vapor is 2. Other ones down here, sometimes these will have to be given to you. I think the other ones likely would be as well, but liquid water for sure, definitely know that one. Okay, all these other substances change their temperature much easier. So like lead down here, 0.13. If I add a little bit of heat to lead, its temperature is going to change very, very quickly. Water is going to be very resilient and not change temperatures so quickly. If 2 reactants at the same temperature are mixed and the resulting solution gets warmer, that means the reaction is exothermic. So if I mix 2 substances together, an acid and a base or something, and it makes like the temperature of the solution increase, it's exothermic. Exothermic releases heat into the surroundings. It warms things up. Endothermic are opposite. They cool off the solution. Okay. That's kind of a side thing. I think I was in the wrong order. Doesn't matter. Okay. Specific heat capacity. You can calculate how much the temperature will change when you're not going through a phase change. We'll come to a phase change in a second. Phase change is like boiling or melting. So this is if we're not boiling or melting or freezing or condensing, I can calculate exactly how much heat I'll need to change the temperature or vice versa. All of our variables here. Q is heat. Q will always be heat. M is mass, makes sense. C is that new constant specific heat. It's 4.18 for water, but different substances have different specific heats. And change in temperature is how much the temperature changes by. So it's final temperature minus initial temperature. It can be in Celsius or Kelvin. Either way is fine. Not in Fahrenheit, though. Okay, so let's look at this example here. How much heat is needed to raise the temperature of 100 grams of water from 45 Celsius to 85 Celsius? Okay, so I'm dealing with heat and changing temperature. To me, that screams I need this new formula. Q equals MCAT. That's the easiest way to remember it. MCAT. Q is my heat. The question saying how much heat is needed. So that's what I'm going to be solving for. To raise the temperature of 100 grams of water, that sounds like a mass. So I'll plug that in for M. C is my specific heat. It told me it's water. Therefore, I know its specific heat. It's 4.18. From 45 Celsius to 85 Celsius. Change in temperature is the one that gets a little bit weird. The way I think about this is temperature 2 minus temperature 1. So my final temperature minus my initial temperature. You could also write TF for T final and TI or something for T initial. If that makes more sense to you, go with that. Either way is fine. Okay, well in this problem, from 45 degrees Celsius, that would be T1, my initial temperature, to 85 is T2. So my change in temperature equals 85 minus 45, which is 40. My temperature increases by 40. So that's the number I want to plug in here. Well, I just have 3 numbers there. That's great. Multiply them together. That'll be my answer. Calculate that real quick. $16,720 joules. Heat will always be measured in joules. or kilojoules, but joules is fine. Okay, that's that problem. Q equals MCAT problem. I can give you any of these. There's technically 5 variables in here. I could ask you to solve for the heat, ask you to solve for the mass if I gave you the heat, ask you to find the specific heat by giving you all the other variables, or ask you to find the change in temperature, which could be either the final or initial temperature. I could also ask you. So there's a lot of different variables I can ask you for those types of problems, and we'll practice those in class. Okay. Next, though, a little bit harder problem. I want to calculate the total amount of energy needed to turn 50 grams of water. Okay. This is talking about liquid water, so I'll give it a little L. It's starting at 50 degrees Celsius. And I want to turn it into water vapor, which would be H2O gaseous. And I want it to be 125 degrees Celsius. Okay, so remember with water, I'm going to draw a little sketch over here. Okay, my melting / freezing point is 0 degrees Celsius. My boiling / condensing point is 100 degrees Celsius. So that means anything between 0 and 100 will be a liquid. Will be regular water. Anything below the melting point, below 0, will be ice. It would be frozen, right? Solid would be the proper word for it, I guess. And then anything above 100 degrees would be a gas. Okay. If I'm just staying inside of one category, if I'm not changing the state of matter, it's just solving like this, a Q equals MCAT problem. What we just did before this, though, is calculated how much energy it takes to boil or freeze or something like that, using this formula, Q equals M times one of the two constants. In this problem here, what we're doing, we are changing temperature and changing states. So let's think about what's going to happen in all of our different steps here. So I'm starting at 50 degrees Celsius with H2O liquid. It's just regular liquid water. Okay. I'm going to add heat to this. So when I add heat to this, this is just at 50 degrees Celsius. It's going to increase until it gets to that first stopping point. So it's going to go all the way up to 100 degrees Celsius, where it is still liquid water. So I'm just warming up the water. This is kind of step 1. Once my water gets to 100 degrees Celsius, okay, then it's going to boil. While staying at 100 degrees Celsius, this is going to turn from H2O liquid into H2O gas. It is going to boil. I can calculate exactly how much heat I need for it to boil. That's going to be step 2. Now I have 100 degrees Celsius water vapor, but my question wanted 125 degrees Celsius water vapor. So I'm going to heat this up until I get to 125 degrees, and I still have water vapor. That's going to be my third step. Okay. So anytime you need to cross the barrier to melt or freeze or something, that's going to be its own separate step. You're going to calculate that much heat. And then this one actually has to warm up a little bit more. So what's going on here? I have a medium temperature liquid. Step number 1, heating it up till it gets to 100 degrees Celsius. That takes a certain amount of heat. Once it gets to 100 degrees Celsius, it needs to turn into a gas. I have to boil it. That takes a certain amount of heat. Number 2. And then number 3, once I have that gas, I actually want to heat it up a little bit more. So I would calculate how much heat that is, would be step number 3. So when we are changing temperature, we use the MCAT formula. When we are melting or boiling, we use the other formula. So let's think how these 3 steps to be calculated. For this first step, I have Q. My temperature is changing. So my formula here is MC delta T. I'm going to throw in the mass of the water, 50 grams, the specific heat of water, and then the change in temperature of water. That's step 1. Plus, I also need some heat for step 2. I'm going from liquid water at 100 degrees to gas at 100 degrees. So this is just boiling. So my math for this one is M times H. I'm going to use the HV because it's vaporizing. I'm going to use my 50 grams of water and throw in the constant for HV to see how much energy it needs to actually make this boil. Once I have boiled water, I'm going to go into step 3, which I'm just heating it up again. So this will be a second MCAT. The temperature is changing. So these 3 formulas, I'm going to solve them all kind of separately, add them all up together. That's the total heat I need to make this change occur. So let's get started with it. M is going to be 50. So this is C. This is liquid water. So the C for this is 4.18. My change in temperature goes up by 50 degrees. So it'd be positive 50. Plus, second step, my mass is 50 still. HV, the latent heat of vaporization of water, is the 2260 number. This one doesn't have a change in temperature or anything because the temperature is staying the same. It doesn't have a little c. You don't need the specific heat in this formula because I'm not changing its temperature. Specific heat is how it changes temperature as you add heat. For the last step, I do need all these things. We're doing another MCAT for 100 degrees Celsius gas turning into 125 degrees Celsius gas. My mass is still 50. My C, I have to be careful. I have H2O gas now. I'm going to go to my chart, find what is the specific heat of H2O gas, which I believe is 2.00. The change in temperature now goes from 100 to 125. That'd be a positive 25 degree change in temperature. I have all my things plugged in. I'm going to multiply them all together and find Q by adding them all up together. First term, 10,450. Second term, 113,000. And then last term, 2,500. One of these is much larger than the other two. This middle term, it actually takes a lot more heat to boil water than it does to raise or lower its temperature. Pretty significantly so, I'd say as well. Add all these together, and I'm going to round my answer. I get 126,000 joules, or you might see it written as 126 kilojoules. They're the same. That is a full calorimetry problem. One more type of calorimetry problem like this, but this is kind of the most important thing. Now think about what is the most number of steps I could give you in a problem like this. Well, the most number of steps would be starting all the way down here, right? Maybe starting with a solid lower than 0 degrees. So maybe starting here. I need to calculate how much heat I need to get up to 0. I would need to calculate the amount of heat I need to boil. Or sorry, that's melt. I need to calculate number 3, the amount of heat it needs to go all the way up to 100 degrees. Number 4 would be the amount of heat I need to boil. Up to number 5 would be however hot I want to make that gas. So a problem like this can have up to 5 steps if you have to change phases twice and then heat or cool accordingly. All right. When a hot object is added to a cooler object, heat will be transferred until they're both the same final temperature. That means the negative Q lost by one thing equals the Q gained. If you add a colder thing to a hotter thing or vice versa, the amount of heat that one loses must be equal to the amount of heat one gains. The heats have opposite signs since one object's losing heat while the other object's gaining heat. We use that for a problem like this. This is a crazy looking word problem. Don't worry, it's really not that bad once we break it down. So I'm going to actually start. Let me draw this picture real quick on my thing. All right, so I'm going to draw a little beaker. Before I even read the problem, I'm just going to kind of copy their drawing. And it had some water in it. And I had a tiny little cube of metal. Okay. So this up here is going to be a tiny cube of metal. and I have an insulated beaker of water. Okay, now suppose a 55-gram piece of metal. So up here by the metal, I'm going to put down my information for it. 55 grams. Is heated in boiling water to 99.8 degrees Celsius. So that's its temperature. Well, that's going to actually be its initial temperature, T1, because no changes happened to it yet. And it's then dropped into cool water in an insulated beaker. So in a moment, after when I'm ready to solve, I'm going to drop this hot piece of metal into this cool piece of water. Okay. The other piece of information I might need is C, the specific heat. Depending on what metal I have here, its specific heat is going to tell you how fast its temperature is going to change. Well, it just says metal. It doesn't tell me which type, which means I don't know its specific heat. If it told me iron or tin or lead, I could go to that chart and find its C. But this time I don't have it, so we're just going to leave it like that. Okay. Assume the beaker contains 225 grams of water. So, water, 225 grams. And its initial temperature before the metal was dropped in was 21 degrees Celsius. That's its initial temperature. Water, though, I do know its specific heat. Water specific heat is 4.18. So here are all my pieces of information given to me from the problem so far. I know my metal's mass and its initial temperature. I don't know its specific heat because I don't know what metal it is. For my water, I know its mass, I know its initial temperature, and I know its specific heat because it's just water. The final temperature of the metal and water is 23.1 degrees Celsius. So, my T2, I'm going to drop this metal into the water and let them exchange heat until I reach a thermal equilibrium. At that point, they'll both have the same final temperature. Heat will continue to flow until the metal and water are at the same temperature. So the T2 actually applies to both of these things. It's 23.1 degrees Celsius. That's the final temperature of the metal and the final temperature of the water. Using this information, what is the specific heat capacity, C, of the metal? Okay, we already knew we didn't know that, so that's what we're actually solving for. We're going to find the specific heat of this metal based on all this other information. This will tell us a property of that metal, which might let us identify what metal it is. A lot of variables here, though. There's actually 7 different variables to keep track of. All right. A problem like this, the main idea, is what we just talked about on the last slide here. Negative Q lost equals Q gained. Okay, so let's think about our example here. The metal, is it losing heat or gaining heat? Well, it's starting off really hot and it's cooling off. So the metal is what's going to lose heat. The thing that gains heat, the water starts at 21, heats up to 23. The water is gaining heat in this situation. Okay? So what we can do, we can set equal to each other. The amount of heat lost by the metal must equal the amount of heat gained by the water. So what we can do is use MCAT. Q equals MCAT. And plug that in for both of these Q's. Now this one has a negative sign. So I'm just going to keep that negative sign in for Q. I'm going to plug in MCAT. This would be the MCAT of the metal. Over here on the right, I have Q gained. I'm going to plug in MCAT for Q. Over here on the left is the negative MCAT of the metal equals the positive MCAT of the water. And now we're just going to plug in. We have most of these variables. The one we're looking for is the specific heat of the metal, this Q, or sorry, that's a C, this C. We have all this other information actually. So let's plug in what we know. So I have a negative sign, don't forget that. Mass of the metal is 55. C of the metal is unknown, so I'm going to leave my C. Change in temperature. Remember, change in temperature equals T2 minus T1. the T2 was 23.1 minus my initial temperature of my metal was really hot, 99.8. Most common mistake is to flip these two numbers. T2 is our final temperature. That goes first, minus my initial temperature. This makes sense. My change in temperature when I subtract these will be negative because my temperature went down. That's also why I need this negative sign here. They're going to end up canceling. On the right side, for water, my mass of water, 225. My C of water is known, 4.18. My change in temperature is temperature 2. So kind of running out of room here, so I'm going to write it a little bit below. Temperature 2 is also 23.1. My T1 of water is 21. This one, my final temperature is higher than my initial because the temperature went up. Let's simplify this again and write it a bit under here. Negative 55C. When I subtract these two, that is a negative 76.7 equals, multiply this together a bit. This is 940.5 times this subtraction is just 2.1. Simplify again in my next step. These two negatives will become a positive, 4218.5 times C. Multiply these two together, 1975.05. C equals, divide, and I get 0.468. That's the specific heat of my metal. That number looks good because it is a small decimal. Specific heats range from about 0 to about 4, so that number looks good. Metals are usually between 0 and 1, so that's a really good number to get. Okay. That's my answer. I have Q equals MCAT for the metal and the water, whichever thing heated up, whichever thing lost. I can plug in all this information to calculate the specific heat. Now, there are 7 variables in here. There's the mass of the metal, the initial temperature of the metal, the C of the metal, the equilibrium temperature, which is shared between both, mass of the water, initial temperature of the water, specific heat of the water. I could ask you to find any of those 7. I'll give you the other 6 variables, just plug them into this equation, and then solve for the missing one. The easiest ones are when there's C or M. It's a little bit annoying with this delta T because one of these two will be a variable. You'll have to do some fancy math and stuff like that, but it's not something we can't do. We'll do some of those in class. That's it. That's the problem. Now, if I go back a couple slides just for a moment, I can compare on this chart and see if my specific heat, which is 0.46, is close to any of these metals. That would be a hint that the metal that is unknown is actually that compound. And look, we have iron 0.45. That's really close to 0.46. So this unknown element was probably iron. Now, it could have been something else as well, but that's a really good hint at a way to identify an unknown substance. The AP exam cares about things like that. Say, what is one way we could find the identity of an unknown metal? By doing a calorimetry test like this. And we will be doing this live in class as well. Okay. A couple more problems, a couple different ways to talk about enthalpy again. So that's it for calorimetry for now. We have Hess's law first, and then we have one other way, enthalpy of formation after that. In going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. In other words, the heats of reactions are additive. When we talked about multiple mechanisms of reactions for rates, you had to multiply together all the rates at the end to get the final rate. It's not the same for enthalpies. When you have multiple enthalpies, a multiple step reaction, you just add them all together. That makes it a little bit confusing. We'll review the kinetics things later, but like for now, we're just adding up all the different enthalpies together. So here's what I mean. This top reaction is the one I want to know. If I add N2 and 2 O2s and make 2 NO2s, the heat of that is 68 kilojoules. This reaction can be carried out in 2 distinct steps with enthalpy changes designated by H2 and H3 here. So I have this step and gaseous nitrogen, gaseous oxygen making NO. nitrogen monoxide. 2 of those nitrogen monoxides with oxygen making NO2. These 2 reactions, when you add them together, cancel out to make this. Okay, here are their independent enthalpy values. If you add them together, they just equal this reaction. Okay, the enthalpy change of this is equal to adding these 2 together. Okay, so if you have multiple enthalpies and you add them together, you get the total enthalpy for the whole reaction. That's basically what that means. Okay. A couple of manipulations that we might need for a problem like we're about to do. If a reaction is reversed, the sign of the enthalpy is also reversed. So if you flip a reaction, make it a negative, or if it's already negative, make it a positive. Flip the sign if you reverse a reaction. A lot like what we were doing with some other things before. Before, though, when we did it with kinetics, we inverted it. Or when we did with equilibrium, we made it the reciprocal. This one, we're not worried about the reciprocal thing. We're just flipping the sign of the enthalpy. The magnitude of H is directly proportional to the quantities of reactants and products in a reaction. Okay, what that's going to mean for us, if the coefficients in a balanced reaction are multiplied by some integer, the value of H is also multiplied by that number. So if you have to double everything, you double H. If you have to flip the reaction, negative H. Okay. So let's look at an example here. We're going to have the following data. 2 fundamental reactions, 2 small reactions. I know their enthalpies. This one's 46 kilojoules in this reaction. But remember, it's with this exact set of coefficients. Negative 484 for this reaction. Given those 2 pieces, I want to calculate for this entire large reaction what its enthalpy is. I'm going to manipulate these so that when I add them together, I get this reaction. Also keep in mind I need to manipulate the enthalpies, and then add those together to get my final. Okay, so just a minute to write these 2 down. Let's get into the page. Pretty long problem. Okay, so starting, I have NH3. To save time, I'm not writing out the states of matter. They could matter if it like changes from solid to a liquid or something like that. That'll come up a bit. Okay, so my enthalpy of my first reaction here is 46 kilojoules. My second one is negative 484 kilojoules. So just to review, this one is an endothermic reaction. This one is an exothermic reaction. Okay. The reaction I want to find, though, it's cut off on your screen, that's okay, is 2N2 plus 6H2O making 3O2 and 4NH3. Okay, so given these 2 parts, what I'm looking for is the enthalpy of this reaction I constructed. These have parts that are found in here, but it might not be exactly completely obvious how they add together. So I'm just going to start one at a time. I'm just going to start with this first reaction. We'll look at NH3. There's NH3 in this reaction as well, but it's on the other side. So I'm going to have to flip this reaction. I also notice there's 4 of them. So I'm going to have to flip this and times by 4. So I'm going to flip it first. I'm just going to rewrite this one down here. When I flip it, I get 1/2 N2 plus 3/2 H2 gives me NH3. Okay, but I had to flip it, so my enthalpy started at 46. It is now negative 46. Doesn't match up yet. Like I said, we have to multiply this entire thing by 4 to get to 4 NH3s. So we're going to have to multiply this by 4 as well. Multiply all this by 4, this equals 2 N2s plus this is 6 H2s gives me 4 NH3s. The enthalpy of that, negative 46 times 4, is negative 184. That sounds right. Kilojoules. Okay, so this is my first reaction. Some of the things matched. Remember, this is the reaction I want. The N2s match. I have 2 on each on the right side. I have 4 of these, but the H's don't actually fit in anywhere, so those hopefully are going to cancel out later. And then I also don't have the H2Os or the O2s, so we need the second reaction for that. Okay, so The H2s, like I said, will hopefully cancel out with these, but they're not the final. So let's just skip it and move on to the next thing to make it easier to see. O2 is next. Okay, so this reaction has O2 on the left. This side has it on the right. So I'm going to have to flip this reaction around. Then I also have 3 O2s here and only 1 here. So I'm going to flip it and times it by 3. So I'm going to rewrite it down here, what that'll look like. So let's flip it, and I'm just going to times it by 3 at the same time. So this is 6 H2Os. Goes here, times by 3. Creates 6 H2s. Flip this side, plus 3 O2s. My enthalpy, I'm going to flip its sign, so now it's positive, and then times by 3. Is 1452 when I did that. So I think I have these two reactions. Might not be obvious that it's going to make this, so we're going to check our work. We're going to add these two together. All the things on the left side, all the things on the right of the arrow on the right side. Anything that's on both sides and equal, I can cancel, like these H2s. 6 on the left, 6 on the right. Add everything else together. 2 N2s plus 6 H2Os. Add these two together. I'm going to write it in the same order that it is up here. 3 O2s plus 4 NH3s. So these manipulations, adding them together, gets us our final reaction. So what's the enthalpy of our final reaction? Well, it's the enthalpy of 1 plus the enthalpy of 2. This is 1, this is 2. I didn't really label them. It's negative 184 plus 1452, which is 1268 kilojoules. You can find the enthalpy of a full reaction given its kind of starting components here. To manipulate the enthalpies, if you flip the reaction, you change the sign. If you multiply by a factor, you multiply the reaction by the same factor, or the enthalpy by the same factor. Okay, one more topic, then we'll be done. Our last topic is the standard enthalpy of formation. You'll have this delta H with a little F, which stands for formation. The little circle means standard, that means like per mole. Okay. Change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. This little table on the right is a standard enthalpy of formation. That means this is how much energy or heat it takes to make this thing, or how much energy is kind of contained in its bonds. Is another way to think about it. So have all these different compounds. You'll notice most of them are negative numbers. That's because bonds are usually stores of potential energy, and that negative number is how much energy is being saved when that bond is formed. Positive number means it actually takes a little bit of energy to make that bond. So NO2 actually takes a bit of energy to make. So I'd expect it to be an endothermic reaction. It takes a little bit of energy. Okay, so this, you can look up charts of all the enthalpies of formation to different substances, how much energy it takes to make them, basically. For compounds, it'll always be a number. Okay? For a compound, for a gas, we assume it's exactly 1 atm of that gas. For a solution, 1 molar. For a pure substance, liquid or solid, 1 mole. Okay. For a compound, you use the numbers on the table. Now, if you have a free element, so something like N2 or K, its heat of formation is 0. So any pure substance that's not a chemical bond is not going to have any heat of formation. It is going to be at its standard 0. So this is kind of like, enthalpy of formation is weird. It's kind of like the energy you need to make compounds, or the energy change associated with making compounds. If you have a free element, it's not a compound, so it is 0. If you have something like N2, that's a diatomic molecule. It's another free element form. It is 0. Okay. I'm going to use that for this crazy looking reaction. I'm going to rewrite it on the problem we're about to do in a slightly simpler way. I'll give you a second to write this, but what this means is enthalpy of the entire reaction equals the sum times their coefficients of the products times the change in enthalpy of formation of the products minus the sum of the coefficients of the reactants. Okay, it looks really dumb. In fact, I would just write it like this. So the change of enthalpy for the entire reaction, Rxn stands for reaction. So this is the standard enthalpy for an entire reaction is equal to the sum of the products, and it's really the sum of the enthalpy of the products. So I should write a little h minus the sum of the enthalpy of the reactants. That's how I think about this formula. It's still annoying, but it's way simpler. So the sum of the products means you're going to add up the enthalpies of all the products. So maybe like C is a product, and maybe D is a product. You're just going to add all those up together. You're going to subtract it from the enthalpy of all the reactants. So maybe A is a reactant you started with. You're going to sum that up with maybe B is a reactant you started with. And that's what it's going to look like. Take the enthalpies of each individual thing, add together the products, subtract it from adding together the reactants. That looks way too confusing. I'm going to show you this in a problem real quick. And that's our last slide, actually. I want to find the enthalpy change of this entire reaction. Okay? So the enthalpy of this reaction, I'm going to write it down. 2 NAs plus 2 H2Os makes 2 NaOHs and H2 gas. Okay. I have this little chart for you on your worksheet as well. These values are nothing you need to know. They will be given to you. But you notice there's only 2 of them, so we'll talk about why. I want the heat of the reaction, enthalpy of the reaction, sum of my products minus my sum of my reactants. So my products, I like to put it in brackets like this. So I'm going to have all my products here minus my reactants here. The reason I'm going to have it with lots of parentheses and stuff here is so that I keep my signs straight. Especially since there's a minus here, the signs might get a little messy. So I'm just going to start with my products. So NaOH is first. That has a 2 in front, so I have to multiply by 2. Okay, because I'm making 2 of these. NaOH's number is negative 470. Okay, just go to the table, find its number, negative 470. Plus, because I'm summing together all the different products. That takes care of this first one, though. H2. H2 is not on your table, but it does not matter because it is a free element. It is not a compound, so it is 0. So this is going to be plus 0. Anything that's a free element, kind of like with oxidation states, oxidation states always 0, so is their enthalpy of formation. Then I'm going to subtract from my reactants. So I'm going to start with 2 times Na, solid. Na is also an element. Its enthalpy of formation is 0. So this is 2 times 0. Plus, my second one here is 2 H2Os. So that's going to be 2 times H2O. The states of matter here because if you look at a big chart, there's going to be one for the solid, the liquid, and the gas. Okay, so my H2O liquid's given to me in the chart. That's this negative 268. I have the 2 in front because I have 2 of them being used in the reaction. If I add all this thing together correctly and subtract them correctly, that is my answer. But it can be tricky, and the most common thing to mess up is the signs. Just be very careful with your signage. So I'm going to leave this whole thing in brackets until I get the full number, and then I'm just going to subtract them. So this one, 2 times negative 470, it's negative 940 plus 0. For here on the right, I have 2 times 0 is not 2. It's in fact 0. Plus 2 times this is negative 536. Right, over here, this adds together to equal negative 940. This adds together 0 plus negative 536 is a negative 536. So a bunch of negatives here, which is why it can get confusing. This is negative 940 minus negative 536, which is really just plus 536, equals negative 404 kilojoules. We're going to do some problems like that to practice. You need those data tables. This is basically for this entire reaction, the overall enthalpy of the reaction. So this is what's the total heat change when I start with these reactants and make these amount of products. Okay. This can be used to predict if the reaction is endothermic or exothermic as well. Negative, so this is exothermic. This is going to release heat. This is going to add heat to my surroundings. Okay. That's it for Unit 6, Thermochemistry. The next 2 units correlate very heavily with this. We're going to learn about the other 2 thermodynamic quantities, entropy and Gibbs free energy. There's going to be very similar looking reactions and stuff like that for those. And then we're pretty much at the end. So hope that a lot of that made sense. If not, let's practice it in class. So have a good day, everybody.